modeling principle, and I'll give an example starting from very basic principle of modeling and say mechanical system, and we will get introduced to the concept of analogous system, not analog but analogous system. That means there is some similarity between a class of systems in a sense that they can be represented in an unified manner, that is by a single form of differential equation can be enough to describe a set of different plants, and that may not only include mechanical or electrical or fluid system or thermal system. It can be any system, but they can be represented by an unified set of equations, okay, irrespective of their nature, but their representation will be identical. So let us start. So our objective is to obtain the mathematical model of dynamic system. So as we all know that the dynamic system or the practical systems that you normally encounter are rarely simple, and they constitute a lot of non-linearities, lot of discontinuities in their behavior. So it's very difficult, and most importantly lot of interaction. So this phenomena, all these phenomena are very difficult to represent in reality when obtaining a mathematical model. So what is normally done, we first develop a mathematical model of a system based on what is called a model of the system, that is a physical model or idealized model of the system. So in that sense, our first objective will be to obtain the simplified model or the simplified representation of the system and represent that in terms of mathematical equations. Now, before going into that, I should recall that in our course we shall only be considering linear, time invariant systems. The thing is that, again, I should reiterate that we normally rarely find such linear time invariant system in nature. But what we intend to do is to represent any physical system. It may be linear, it may be time varying, it may be non-linear, it may be time invariant, to a model. The model that we want to represent, that model is an LTI model. So obviously there is a question of compromise. That is how much compromise you're making in terms of accuracy to achieve a simplicity or to facilitate your modeling process. Obviously, there is a point of argument that you can argue that why should you represent a nonlinear system by its linear model. So I'll try to address this issue later in the class. But we should always keep in mind that to start with, what we intend first is to develop a qualitative idea about a system. Then, as for our requirement, you can go for quantitative analysis. And it is seen that to achieve or to obtain a qualitative idea about a system's behavior, a linear time invariant representation is enough. In a sense, it is much easier to obtain, it is much easier to analyze because a plethora of tools is available to study such LTI systems and consequent design of controllers for LTI systems. But the problem that you may face is that the actual plant behavior and the behavior of the model that you have developed by assuming it to be an LTI system will differ by a considerable margin. So in that case, what you next intention will be to improve your modeling, that is to incorporate some of the phenomena that you have ignored in the first level of modeling. So you incorporate some of the non-linearity. So your mathematical equations will no longer be linear time invariant, rather it will be more involved. Considering non-linearities will come into picture, some time invariancy will be removed and time varying terms will come into the picture. So it will gain in complexity, but on the other hand, it will obviously will give you more accurate prediction of the dynamic behavior of the system. So if you continue with this in an iterative manner, you might argue that at a time we'll reach an accurate model of the plant. Yes, you can achieve that, but there is always a situation where we achieve a point of diminishing return. That is where the improvement in accuracy by introducing some complexity or incorporating some complex behavior of the plant is very very less as compared to the mathematical computations that is getting involved in obtaining that complicated model. That is, the complications that are associated with a slight improvement in accuracy is too much, right? That is, by incorporating lot of complexities in your mathematical equation, what you're gaining is a very small amount of improvement in accuracy. On the other hand, your mathematical computation in terms of developing the model and in analyzing the model or predicting the behavior is so labored and so cumbersome and so complicated that it is called a point of diminishing return. So we have to stop at that point, because moving any further will not get any significant improvement. On the other hand, will involve more mathematics. So obviously you have to strike a balance between your accuracy and your simplicity, and that is why this modeling is kind of an art. Okay, that means you have to strike the right balance between this accuracy and simplicity. So with this in the back of our mind, let us start with our modeling. So our objective will be to develop a linear time invariant model, and for dynamic system this will lead to differential equation, and I should emphasize ordinary differential equation with constant coefficients that we already seen. So this is where we intend to reach. Now in this path of a modeling, then we have to face a lot of difficulties. So what are the difficulties and how should we proceed in this path is very important. So to obtain this differential equation model of a physical system, we have to take some assumptions and we have to follow a particular path. So, in this lecture, I'd like to present a method of obtaining the differential equation model of a physical system which utilizes the physical laws of the process. Okay, some fundamental physical laws of the process. So, in this regard, the first step to build up a physical model of the system. So, this physical model is not any ordinary physical model. As an interconnection of idealized system elements. This is very important. What is or what are the idealized system elements, and describe them in the form of elemental laws of, I should not say physics, elemental laws. It may be physics, biology, chemistry, or you can say from the first principle perspective of the first principle. So we should first identify what are these idealized system elements, right? So you can say an ideal element. I don't remember whether I've discussed this or not, so I'll go through very quickly. Should follow to basic assumptions from two basic assumptions. What are two basic assumptions? Number one, the spatial distribution is ignored. That means it is regarded as an point phenomena. For example, we consider the entire mass which is distributed over space to be concentrated at the center of mass. A temperature in a room which is distributed over the room can be considered to be the temperature of the room at any convenient point in the room. So this is the point phenomena. Similarly, the resistance, which is distributed over the length of the conductor, is assumed to be concentrated at a particular point as a lumped resistance. So this point phenomena, this kind of operation is called lumping, and the corresponding model is called lumped parameter model, right? So this is one thing. On the contrary, there may be situations, especially in chemical processes, where you cannot consider this assumption because the chemical reaction is variable with respect to distribution as well. So in that case, it will be, just for the note, a distributed parameter model, and such distributed parameter model is described by partial differential equation, because this model is function of both displacement and time, whereas this is function of time only, the lump parameter model. We have not considered the distribution of variable over space, right? Another second assumption, this is the first assumption, so we assume the element to be lumped or considered to be a point phenomena. The second assumption in this regard is that the variables associated with the ideal elements lie in the range so that they can be expressed as, or expressed as na, by simple linear laws of, what the laws, a constant of proportionality B, a first order derivative, and C, a first order integration. That means it can be kx, kx dot, say k1x, k2x dot, k3x double dot. Oh, sorry, not x double dot, right? So this is another assumption. So taking these assumptions into account, now let us develop or let us consider a few examples where we are dealing with some idealized elements or ideal elements. So in this regard, let us first consider a mechanical system. So there may be two types of mechanical system: translational and rotational. So what are the basic components of such mechanical system? Mass or a mass element. So in this case, say we have a mass element like this, and this is a reference. And if we apply a force over here, and that gives a displacement x and velocity v, and this is a reference, and this is your force, then how can we represent that? We can represent F as mx double dot or mv dot, right? Similarly, let us consider the second element, that is a spring element. So for a spring element, I'm applying a force F over here. So there will be two sets of displacement. Say this end has a displacement x1 with velocity v1, and this end has a displacement x2 with velocity v2. Then we can write this F as k x1 minus x2, or x is a relative displacement between these 2 points, or integration, right? And finally we can have a damper element. We apply a force F over here, to v2. So you can write this F to be, say, some constant F into 1 minus v2, that we define as F v, right? So these three are the ideal elements associated with a mechanical translational system. And obviously this assumption is that they are lumped and they follow simple law of integration, first order derivative, or constant of proportionality. Their rotational counterparts will be an inertia element. Say it is J, where we applied a torque T, which produces an angular displacement theta with angular velocity omega. So we can simply write this T as j omega dot or j theta double dot. Next we have torsional spring. We have a torque over here, and say this side has an angular displacement theta 1 with a velocity omega 1, and this portion omega 2. So you can simply write this torque to be theta 1, or defined as k of theta. And finally, a damper similar to that linear case. So these are the basic building blocks of a mechanical system, and the corresponding representation of the variables associated with this. And so this is, so what you can write, same, that t will be equal to f into omega, right? Now I want to just make one observation. See, this equation, the relation between force and displacement or velocity, this gives the relation between torque and the angular displacement or angular velocity. This gives for the spring relation between force and the linear displacement. This gives the relationship between torque and the angular displacement, force and torque and angular velocity, force and linear velocity. Right? So these are the elements under consideration. Now, among these elements, I think this has already been covered in the other part. There are certain elements which are energy storing elements. That is, the energy can be stored or retrieved without loss, which are called the conservative elements. In this case, the conservative elements are mass and spring, and there are certain elements which can only dissipate energy. The dissipative element. In this case, the damper is a dissipative element. Right? Okay. With this in mind, let us consider a system that comprises of this basic building blocks or basic ideal elements. First, let us consider a translational system. Mass M, and on application of force F, I have a displacement. This is x equal to 0, x in this direction, and this has a stiffness F and a viscous friction coefficient F. So what I have to do, I have to draw the free body diagram of the mass. Then What are the force component that is acting? F 0, and we have this spring force kx, and this force F extra, and the displacement is x. All of you agree with this?
Yes, sir.
Are you sure? Is that anything missing or not?
So the inertia part is missing.
No, no. Where should be inertia come? This mass only, na? That inertia means okay, yeah, yeah. That m d2 ct square is missing. Fine.
Yeah.
And what about the mg component? What is the mg
So
component?
mg will be balanced in the static portion when the mass will be released from its initial position. The kx will be balanced with mg because
Right. The point is that yes, you're correct, but I should explain to the class that whenever you're considering this system to be in an equilibrium position, before you apply any force, equilibrium position means a point where every force is balanced. So the mg portion of the force will be exactly counterbalanced by the force produced by the spring and the damper. Right. So for a typical example, suppose the spring to start with as a length under unstretched condition of say 1 feet. Now as soon as you suspend the mass to counteract the weight of the mass, the spring gets elongated by say 0.1, 0.5 inches. So the spring length has now become 12.5 inches, and that point is called, or that point is regarded as point of equilibrium. Now when we apply the force, the spring will elongate beyond that 12.5, or or get squeezed below the 12.5 range. So the effective spring length, if you consider to be 12.5 inches, then the mg component of the mass is already taken into account by this zero point 0.5 inch elongation of the spring, say. So from equilibrium point, from a point of view of equilibrium, the mg component is already being taken into account. So now once you develop the free body diagram, the mg component need not be considered. Fine. So if I now write down the force equation, so applying the Newton's law of motion for the free body diagram, you can write down, see, F minus Fx dot minus kx, right? Or rearranging, right? So this is a simple mechanical system involving translational motion. What about rotational motion? Let us consider rotational system on the same page. So now rotational systems are very common because whenever you're dealing with rotating machineries, we have to consider this. That is, there is any system that involves a fixed axis rotation. So, we consider this with the axis. So, at any point of time, we can consider that this shaft of stiffness k and an inertia j is rotating in a viscous medium with viscous friction coefficient F under the influence of a torque T that produces an angular displacement theta and an angular velocity, say omega. So if we draw the free body diagram of this, I'll not take the chance of drawing that from isometric view. Let us draw this. It's very difficult to draw these lines of this pen tablet. Anyway, so we have this torque acting like this, and this spring stiffness will act in this direction, value k theta, and this viscous fluid will produce an opposing force in this direction, F theta dot. So at the end of the day, we can write down the torque equation as T minus F theta dot minus K theta is equal to J theta double dot, or you can write J theta double dot plus F theta dot plus K theta is equal to T. So this equation describes the dynamic behavior of this system. Now, what is the similarity between these two equations? See, this is a linear differential equation with constant coefficients. What is the order of the differential equation? Second order differential equation, because each of them constitute two energy storing elements: spring or the shaft stiffness, and the mass or the inertia. Right. Now, just keeping this in mind, let us get back to the basic or fundamental electrical systems. Right. Say RLC series circuit. Well, dealing with RLC series circuit, if we just remember, we have a source E over here, and so this is your R, L, and C, and this is your, so E0 is equal to capacitor voltage. So for that, you can write the KVL as L di dt plus Ri, where I is a current, plus 1 by C integration I dt is equal to E. Now we know that charge stored in the capacitor can be represented as, right. So from that we can write I is basically dq dt. So if we replace this and this over here, then this equation simplifies to LQ double dot plus RQ dot I think all of you can follow. Then RLC parallel circuit, let us consider. So in that case, let us consider a current source I, which is exciting R, L, and C connected in parallel. And if we apply KCL at this particular node, then you can write that if this voltage is E, then you can write the current, total current is equal to the current through resistance, that is E by R, current through inductor, plus the current through the capacitor. Now we take another assumption that we know the flux linkage is associated with the induced voltage by the fact that E is equal to d phi dt, or phi is equal to integration E dt for inductor. So replace this over here. So what you can get, you'll get C d dt, that means C d phi dt, C phi double dot, C phi double dot, plus 1 by R d phi dt, plus 1 by L phi is equal to I. Right. Now just take a look at the similarity between all these differential equations, right? Like mechanical translational system, mechanical rotational system, series RLC circuit, and parallel RLC circuit. Now, if we summarize all these things, then we can observe a very typical phenomenon. Say RLC series circuit, what you have the equation L Q double dot plus RQ dot E. Okay, then mechanical translational system, what you have the equation that M x double dot plus fx dot plus kx is equal to f. Similarly, for mechanical rotational system, what do you have? J theta double dot plus f theta dot plus k theta equal to t. And on the other hand, for parallel RLC circuit, we have the equation. Sorry, C phi double dot 1 by phi dot plus. So in each of these cases, this voltage, this current, this force, and this torque, these are the driving functions, right? And these are the functions, or these are the sources of energy which is responsible for the dynamic behavior of the system. And just by a simple observation, you can say that all these four differential equations have a similarity, that they can be represented as a, I was x already, so y double dot plus by dot plus cy is equal to, say, d, in this form, each of them, where a b c and d are, a b c are constant, d is the driving function, and y is the variable associated. So the concept that we introduce here is a concept of analogous system, and this is a very very important aspect of systems theory, which is a major part of the control system. That is, given a differential equation of this form, It may represent either an electrical system or mechanical system or a variety of systems. It should not be restricted to a particular system. Rather, it represents a class of systems. Now, what is the advantage of this concept of analogous system? See, suppose you want to study a mechanical system, a mass spring damper system, or a rotational mechanical system, which we have discussed. So, you want to understand if I change the mass, or I change the spring constant, or the damping coefficient, if it changes, how the response will behave. So, what you have to do, you have to get a physical model of the mass. Fine, you can achieve any mass, spring, and damper to achieve a very accurate value of spring constant or viscous friction coefficient in physicality or in practicality is really difficult, right? You cannot be that accurate. So what we can do, on the other hand, we can precisely achieve a resistance value, a capacitor value, or an inductor value because the components are easily available. First, second, it is not always possible to develop a physical model involving rotational parts or even translational parts. It is not readily available. The various sizes of mass, spring, or dashpot may not be available with you. But what is available with us is series circuit. On a Vero board, you can easily simulate a RLC series or parallel circuit. Voltage source is easily available. You can design a current source. So, what I'm tending to say is that any physical system, be it mechanical or any other, if you represent it by an analogous electrical system, then you can simulate the system via Vero board or a small experiment based on R, L, and C components. So you can get a physical insight, right? So that is why this concept of analog simulation and the analogous comes into picture, and that leads to what is called an analog simulation, where you can simulate any mechanical system or electrical maybe, or thermal system, fluid system, by an equivalent electrical system, right? So that is the concept of analogous system, and it represents a class of system which can involve any kind of system, right? And the major advantage is that you can, once you achieve the electrical analogous, then you can vary any parameter as per your wish, and you can interpret the variation in R, L, and C as the variation in mass, spring constant, or damping coefficient, right? So that is how we can represent a mechanical or system via an electrical system. So to facilitate this study, let us obtain a set of analogies. That is, first, force voltage and force current analogy. So we can write this as force or torque voltage and force or torque current analogy. Now, how for any mechanical system, what you can write force, or for rotational system, and writing that in a bracket, it should be torque, right? Now, for force voltage analogy, we shall consider series RLC circuit. That is this equation. So the force or torque will be represented by potential, right? Then mass or inertia, that will be represented by inductor. Then this viscous friction coefficient, which is considered F in both the cases, will be represented by Fr. The spring constant, which is considered K in both the cases, will be represented by 1 by C. And most importantly, this displacement, that is x or theta, will be represented by q. And similarly, I just annotate over here, x dot or theta dot will be represented by current. I'm just noting out. So force, voltage, mass, inductor, viscous friction, resistance, spring, 1 by c, displacement as the charge stored in the capacitor, and the velocity as the current. Similarly, for force current analogy, this force we have to apply parallel RLC circuit, because the driving force is now current, right? So obviously the force will be current, mass will be capacitor, right? This F will be 1 by R, viscous friction coefficient will be 1 by R, this spring constant will be 1 by L, and the displacement will be flux linkage, and x dot or theta dot will correspond to what? The voltage, or E I should write. So by this way, you can represent a mechanical system either in the form of a series RLC circuit, where the applied voltage will represent the force or the torque, the inductance of the circuit will represent the mass or inertia, the resistance of the circuit will represent the viscous friction coefficient, the capacitance or the inverse of the capacitance will represent the spring constant, and the charge stored in the capacitor will represent the displacement, and the current in the circuit will represent the velocity or the rotational velocity. Similarly, if you want to represent a mechanical translational or rotational system by a parallel RLC circuit driven by a current source, then your current will represent the force or torque, capacitance will represent the mass, the inverse of the resistance or the conductance will represent the viscous friction coefficient, the inverse of the inductance will represent the spring constant, and the flux linkage will represent the displacement, and the voltage, since it's a parallel circuit, the voltage across any element will represent the velocity or angular velocity. So by this way, you can see that we can represent any equation which is analogous, in a sense that it can be represented in this form, where a, b, c are constants and d is a driving function. It can be equivalently represented by a series or parallel RLC circuit. So that is why it's called a force voltage analogy or force current analogy. That is MBK or MFK to RLC, right? Mass, viscous friction coefficient, spring constant to resistance, inductor, capacitor. Okay, so we'll just recap this by an example. So we have already seen that translational system, given a translational system like this, with mass m, spring constant k, this is spring f. If we apply a force capital F with displacement x in this direction, so we already developed the equation F is equal to mx double dot plus Fx dot plus kx. Now I want to develop the force current or force voltage analogous to this mechanical system. Right. Now the rule is that I just write down the rules. Each junction in the mechanical system corresponds to a node or junction or a closed loop, depending upon whether you are going for force voltage or force current analogy, which consists of electrical source and passive elements, which is analogous to mechanical driving forces and passive elements. Right? Passive element means if you have a mass, a spring, a damper, then it will be represented by passive elements such as R, L, and C. If you have any driving function in the mechanical system, it will be represented either by voltage source or a current source. Next rule, all points on a rigid mass are sorry, considered as same junction. Okay, so all the points on a rigid mass are considered as a same junction. Okay, so in this case, in this by this method, we can obtain. We have already derived that how this force voltage or force current analogy can be obtained. So in this sense, if I draw the Fi analogy, in this case, what we'll get for each and every mechanical junction, we'll get a loop. Okay, so there are three junctions. See, one, two, and the point of mass is over here. So what we'll get a driving function force over here, and for each of these three components, this is your resistance component that will gives us to the 1 by f. Then suppose we have the capacitor, and finally we have the inductor. Now if we get back to the same equation over here, so the resistance gives 1 by f, inductor gives 1 by k, and capacitor represents m. 1 by f, the inductor, what was inductor name? The inductor gives 1 by L equal to k, so L equal to 1 by k, and the capacitor is same as the mass, and this current will represent F, right? Similarly, if we obtain the force voltage analogy where we have a voltage source in series with a resistance and inductor and a capacitor, we can say this represents the force from here. See, E, mass L represents M, R represents F. This represents M, R represents the viscous friction coefficient, right? And the capacitor represents 1 by K. 1 by C equal to K. So capacitor represents 1 by K. So I can simply write down these values since you know what is A, what is M, and what is K for a given mechanical system that you want to model, and you put that into the corresponding R, L, and C values. Right. Now let us take a bit involved set of situation or involved situation where we have interaction between different components. And the two mass that we have here are M1 and M2, and the viscous friction coefficients are F2 and F1. This spring has a stiffness K, right? And we have applied a force in this direction such that the relative displacement of this component is x1 with u1, and this mass 22, right? Now obtain the free body diagrams. Say for mass m2 that we have here, we have a upward pulling force, this spring k, and displacement is x2, assuming this to be the 0 point, and this damper will produce a force in upward direction F u2 minus u1. And similarly for mass m1, I'm not writing the inertia part over here. The forces acting are F, and this force, that is F2 u1, and this force should be F1, I guess. F1 u1 minus u2, right? So write down the corresponding equations for m1. You can write this mass m1. The inertia part I can write is as I'm writing in terms of u1 dt plus f1 plus f2 u1 minus f1 u2 is equal to f for mass m2. Are you right? That m2 u2 dot, the motion is considered to be in a downward direction, so it will be minus f1 u1 plus f1 u2 plus k. I'm writing everything in terms of u1 and u2 because this force voltage analogy, this u represents current, right? So I will develop a force voltage analogous model first. Just a second, I'm getting a call. Sorry. Now coming back to the force voltage analogy. To obtain the force voltage analogy, we have to represent this system in terms of its equivalent current model. So in terms of this first equation, what you can write down, see, sorry, m1, just a second. Hello, হ্যাঁ বলো। ও আচ্ছা আচ্ছা, আর হ্যাঁ কালকে স্যার সাথে খুব কথা হলো। আর কে এসছেন? আচ্ছা 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 আচ্ছা, ঠিক আছে, আমি ক্লাসের মধ্যে ফোন করে দিচ্ছি। তোমার কতক্ষণ লাগবে আর? ওরে বাবারে। Okay, so if I write down the equations again, now for the force voltage analogy, we know that we can represent this as M1 can be represented as L1 and E1, U1 say I1 IT plus I1 minus R1 I2 is equal to VT, right? Similarly, the second equation, that is M2 U2 dot, I'm just replacing the corresponding variables with the electrical equivalent. 2 dot minus f1 u1 plus f1 u2. So this will be represented as L2 di2 dt plus, sorry, minus this one, minus R1 I1 plus R1 I2 plus K, and K means 1 by C integration I2 dt is equal to 0. Clear? Now let us try to write down this equation or directly derive the circuit. So we have a voltage source V, which suppose produces a current I1. So that current is flowing through resistance R1, R2, and L1, and the resistance R1 is also carrying, from the second equation, from the first equation, is also carrying a current I2. So what I can write is that this is your resistance R1, and R2 resistance only carries current I1, and the inductor L1 carries current I1 only. So I put it over here, where this is I1 and this is your L1. So see, V equal to R1 I1 plus R, uh, R2 I1 plus L1 dy1 dt, and this term is missing, minus R1 I2. I have not considered I2 here. Now look at the current I2 loop. Current I2 flows through inductor L2, resistance R1, and a capacitor 1 by C, or capacitor C. So what I can do for current I2, I can augment this with L2, because I2 is only flowing through L2, and the capacitor, and the direction is to the opposite of I1. See, now for second loop, total voltage source is 0. We have L2 di2 dt, and this branch has minus R1 I1 in this sense, plus R1 I2 in the R1 I2 in this sense, and 1 by C I2 dt. So this is the equivalent force voltage analogy of this mechanical system, where this L1 represents mass m1, L2 represents mass m2, this R1 represents F1, viscous friction coefficient F1, R2 represents F2, the capacitor represents the inverse of the spring stiffness, that is 1 by K, and this represents the force F. And I1 and I2, they represent the displacement U1 and U2. Now, you understood this?
Yes, sir.
And I've derived this circuit by observing these two equations. And it satisfies all the rules that I already mentioned. So if you want to develop the model based on the rules, it is very difficult. So it is rather easy to write down the equations and then convert or replace each and every mechanical component with its electrical equivalent. Okay. Now, if you want to obtain the force current analogy, then how can you obtain that? So, if you write down the mass equations again, for M1, our mass equation is U1 dot plus F1 plus F2 U1 U2 is equal to F. And for mass M2, what we have is M2 U2 dot U1. Thus, we already derived from the given mechanical configuration. Now, if we want to achieve the force current analogy, I have to represent this system in terms of its equivalent component. Say for the first equation, m1 u1 dot f1 plus f2 u1 f. From the current analogy, we know this m should be replaced by c1, and this u1 can be represented by the velocity, that sorry, the voltage v1 dot or u1 dot. I'm not saying as u1 dot, u1 dot plus this, see, theta dot or x dot, whatever we say, that is u or omega is replaced by e. Fine. Now the f1 or f is replaced by 1 by r, right? That is the only thing that we have. So instead of writing 1 by r, I'm just writing g, that is the conductance. So this will be g1 plus g2, corresponding voltage e1 minus g1 e2 is equal to I. So current analogy. So this is one set of equation. Here we have a node E1 and a current source I. I should not write I1. And from the next set of equations, what we have, M2 U2 dot minus F1 U1 F2 U2. So from that you can write C2 E2 dot minus G1 E1 plus G1 E2 plus this K will be 1 by L integration V2 dt is equal to 0. Right? Now let us try to develop the circuit. So first we draw the current source that we have, I. Now this current source which generates a current I is flowing through a set of components, and see this C1 I1 E1 dot, that means if you have a polarity E1, suppose I have a polarity E1, then this indicates, so there is a capacitor with a capacitance C1 that causes a current C1 E1 dot to flow, right? The current through this will be C1 E1 dot. Agreed? Now this again causes a current G1 into E1. That means there is a resistance that causes a current, sorry, E1 into G1. So this part and this part is taken into account. No, the problem is that there is a G1 plus Z2 into E1. So that means, and G1 E1 G1 E2. So G1 should be common between these two. So I cannot write G1 over here. Rather, since G1 is common in both the equations, so G1 is only linking. So I have to write G1 like here. So what is the current? Basically, the current flowing through this, if we write down, is G1 E1 minus E2, right? G1 into E1 minus E2. So if you have a potential E2 like this, so the current flowing through this will be, so that constitutes this part. Okay, so this is already covered up. And what is left is G2 into E1. So now, so
Yes, sir.
okay, basically this equation is C1 E1 dot plus G1 into E1 minus E2 plus G2 E1 equal to I. This is the first equation. Now, what about the second equation? Second equation says if this is E2, then we have a capacitor C2 connected over here. So the current through this will be C2 E2 dot. Fine. Then we have a current G1 E1 minus E2 with a minus sign that is already there. This component. And finally, we have an inductor L. So what is the current flowing through this? 1 by L integration. Oh, I've written E2. It should be E2. Sorry. E2 dt. That should be equal to 0. So this is the final force current analogy model. And this components, that is, this I represents the force F. Okay. This C1 represents mass M1, C2 represents mass M2. This L represents 1 by K. This G1 represents F1, G2 represents F2, right? And this U1 represents U1, and this represents U2. So given a mechanical system, and just by following this table, we can directly obtain the corresponding electrical equation, and with a careful observation, we can represent that electrical equation in the form of a electrical circuit, either in a series RLC format supplied by voltage source or driven by a voltage source, or by a parallel RLC circuit driven by a current source. So by this way, you can obtain a force voltage or a force current analogy of that mechanical system under consideration, right? So that is the concept of analogous system. Now, just to extend the concept of analogous system from another perspective, I'll give a couple of examples, right? So the first example is a very basic mechanical system that consists of a mass, which can is free to move on this, and this is also. So this is basically a spring, dashpot, and mass system. I should not. I'm getting confused with this small f and small. So I'll represent B system. So this is a spring mass dashpot or damper system, which is mounted on a cart, which is assumed to be massless. So this cart is massless. So only mass here is that mass m over here. This mass is neglected. Now let us obtain a mathematical model of the system by assuming that cart is standing still for t less than 0. The cart was still, right? And the spring mass damper system is also still, that mbk also standing still for t less than 0. Now in this system, given a input, suppose the displacement of the cart is defined by u, and the following an input at time t, at input time t, the cart, একটু লিখে দেওয়া ভালো, at time t, the cart is moved at constant speed, right? Now the displacement of the mass is measured as y. So you can consider u to be the input and the displacement of the mass to be the output. And this displacement is suppose measured with respect to a fixed frame of reference, right? Say that is somewhere here. So both the displacement are measured with respect to the fixed frame of reference. So and we further assume that the friction force of the dashboard is proportional to the relative velocity across its two terminals, and the spring is a linear spring. So there's a very assumption of a linear spring is there. So what you can say, that total mass or total force equation for this translational system should balance each other. So if you write down the force equation, what you can write down, see, force balance, if you write down the force balance and write for this mass my double dot is equal to this dashpot is proportional, that is force produced by the dashpot is proportional to the relative velocity. So minus of b y dot minus u dot, and this spring is linear, right? So after modification, you can just by rearranging m double dot plus by dot plus ky is equal to bu dot plus ku. So this is the differential equation that represents the dynamics of this cartless, massless cart system that comprises of a spring mass damper system which moves as soon as the cart is set in motion with a constant speed or velocity. Now, given this assumption that initially at t less than 0, the cart and the mass spring damper system was at rest, so we can assume all initial conditions to be 0. There is no velocity, no acceleration, and the point of start or the displacement at that point is taken as to be the reference displacement. Then, with that assumption, if we take Laplace transform of this equation and rearrange them, or say take Laplace transform, what you can get? ms square plus bs plus k ys is equal to us. Or you can write gs is the transfer function between output and input in Laplace domain as, so this transfer function will relate the displacement of the cart with the resultant displacement of the mass due to the displacement u in the cart. So this is the transfer function of this particular mechanical system. Now, on the contrary, let us consider a completely different system, and that system is a car suspension system. Now, typically, if I draw the representation of a car suspension system, it comprises of, say, this is the mass of the car, and this is the center of mass. মুশকিল আছে। This is the center of mass, and as a suspension system, what you have is a spring and dashboard on the front wheel, as well as that on the rear wheel, and this represents the road condition. Right. Now, as the car is moving along the road, so there will be a vertical displacement due to the unevenness of the road. Right. And this vertical displacement as the tires will act as a motion excitation to the automobile suspension system. Right. And that will be in a vertical direction. Now, the basic motion of this entire system consists of a translational motion of the center of mass in the direction of the car, along with a rotational motion about the center of the mass because of the differential motion of these two suspension. Suppose front one is experiencing a speed breaker, so it will be in a upward direction, where the rear one is on a plane surface. So there will be a rotational motion about the center of mass. So mathematical modeling of such a system will be very much complicated. So, in order to obtain a working knowledge, what you can do, we can take a very simplistic point of view. That is, we take a quarter car suspension model. That means you take the model of a single suspension or a single wheel suspension. Suppose this is your mass M, so damper, right? So this point P is responsible. So assuming that motion at point P is defined as xi as an input, and the motion of the mass respect to this is x0, or which is regarded as an output. So if I now write down the equivalent equation corresponding to this system, which is a quarter car model of the entire suspension system, quarter means one fourth. So what I can write down, the force balance, say m x0 double dot plus this is your b, this is k. So b x0 dot minus xi dot plus k x0 minus xi is equal to 0, because here xi is the input, there is no force. The change or displacement of the point P is regarded as an input, and the directions are as shown over here. So, upon simplification, what I can write, mx0 double dot plus bx0 dot plus kx0 is equal to bxi dot plus kxi. Now, assuming that the displacement is measured from the equilibrium position, that is in absence of any displacement xi, so we can consider this as to be modeled at 0 initial condition. Take Laplace transform again, and while rearranging, you can write down transfer function defined as x0s by xis, right? So for each and every suspension system that is involved in each and every car, we'll get a model like this, which is strikingly similar to what we got for this sort of a system as well. Although it represents something from a first impression, it represents something completely different. So, in a sense, we can see that these two systems are analogous from the point of view of our study. Given any input displacement u, in this case, the behavior of y will be similar to the behavior of x0 with respect to the similar change in xi. See, both of them are displacements. Here it is a linear translational displacement in a horizontal plane, where this is the linear translational displacement in a vertical plane. But their mathematical representation or the dynamic behavior is represented by identical differential equation. or identical transfer function. So we can say that these two systems are analogous in respect of the present perspective of study, right? Okay, so I'll conclude today's lecture by giving a final example, because I think once you're studying the dynamic behavior of the system, we should also be very much aware of the fact, or aware about the point of equilibrium, or the equilibrium point, when and how equilibrium point is reached, and the interpretation of the equilibrium point. For that, we'll take help of another example: mechanical mechanical accelerometer. Now, this is a special arrangement which consists of a spring mass dashboard system, and it is housed within a frame which is attached to a moving vehicle. Let me draw. So this is your frame, which is basically attached to the moving vehicle. So this represents the moving vehicle with which the frame is attached, and the displacement of the moving vehicle is measured in this direction. There is a scale for the measurement, and this side also you may have this. So the direction, or the reference direction for this displacement of the vehicle, is this, so x, and this is regarded as a positive side, this is a negative side, and this is your reference point, right? This is a, what to say, inertial frame of reference, this scale. And now within this frame, what we have is a mass, a dashpot, I'll better of writing drawing the hand, and a spring. Better to write this. So K, say B, and this mass M. Now the displacement of this mass is measured on a scale like this, where this is your reference point and the direction is assumed such that this is assumed to be the positive direction. So this is your positive direction, this is your negative direction. Right. So whenever the moving vehicle is accelerated, the frame will get accelerated, which is attached to the moving vehicle, and that will cause the mass to get displaced. This spring will get deflected until it produces enough force to accelerate the mass at the same rate as the frame, right? This deflection of the spring, when measured by the linear motion potentiometer, that is like this, from this, will be a direct measure of the acceleration. That is y measure of acceleration. How can we represent it? Say for that, let us define the variables x. এটাই শেষ টপিক, এটাই শেষ টপিক, এটাই শেষ টপিক। আমি একটু ওভারশুট করে গেছি, আমি জানি। So this is the displacement of the moving vehicle. Y displacement of mass, right? The positive directions are represented here. Now the force on the mass due to spring will be in this direction, ay, and that due to the dash part, because y is in this direction, will be in this direction, by dot, and that due to inertial portion will be this m. Now this inertial force will be a function of the relative displacement of mass with respect to inertial frame of reference, that is note, I should note here, motion of the mass m with respect to the fixed frame of reference or fixed frame of reference in positive direction of y is y minus x, right? So by force balance on the mass, what you can write, force balance on mass, what will yield m y double dot minus x double dot plus a not f plus b y dot plus ky is equal to 0, right? Or you can simplify my double dot plus by dot plus ky mx double dot, or ma, that is the acceleration of the vehicle, a is the acceleration of the vehicle. Now if acceleration is constant, then an equilibrium point will be reached where, or a steady state, y dot and y double dot will both be equal to 0. That means there will be a deflection y, which will be now constant because the spring has deflected by adequate amount so that it produces enough force such that the mass m is now accelerating in the same acceleration or as the frame of the body, right? That is called a point of equilibrium is reached. So if you consider this y dot to be 0 and y double dot to be 0, then from this expression what you can write, ky is equal to ma, or এটা clumsy হয়ে গেল, so that will lead to ky is equal to ma, considering this steady state condition from this equation, or that will typically yield your a as, or you can simply write your acceleration will be given by k. Y is y can be measured from this, right, this scale, right, and from that you can directly measure what is the value of acceleration, right. See, if the body is moving in this direction, it will get deflected in this direction and spring will tend to oppose that motion, and it will produce enough force such that the body, entire frame of body and the mass is accelerated in the same direction, and it's moving in the same direction. So that condition, the equilibrium will be reached. So there will be no further motion of this mass because spring has achieved its required amount of force. So it will be static, and that deflection, say if it is y0, will be a measure of the acceleration via this transformation, and which is a k and m are constant, so you can directly measure the value of acceleration using this mechanical accelerometer, right? So this is how the equilibrium condition should be treated, right, to get the final result of the model, because only developing a mathematical model will not be the final objective. Our final objective is to use the mathematical model to study the dynamic as well as the equilibrium condition or conditions of the system, right? So the one thing that is left that I consider in the next class is the inherent nonlinearities that is present in the system and how you can overcome such nonlinearities. So I'll give an example of a nonlinear spring or nonlinearities involved in other fluid systems or things like that, right? So I'll stop here. If you have any queries or any doubts, you can ask. Okay, fine, fine. So I'll stop here in the class today. So I'm planning a class on Monday since Monday is a holiday. So Monday at say 10:30. Will it be okay? Because I have missed out on two
So
subjects. বলো
Monday সকালে স্যার।
সকালের দিকে এরকম সময়। Okay, I'll schedule that in the classroom by today. If you have any problem, just mention that in the classroom. Otherwise, I'll go ahead with the class. Okay, Monday 10:30. Say okay. Okay. Thank you. So I leave it here.
Thank you, sir.
Thank you, sir.